Each year, Microsoft Research hosts hundreds of influential speakers from around the world, including leading scientists, renowned experts in technology, book authors, and leading academics, and makes videos of these lectures freely available.
It's my great pleasure today to welcome Keshav to Microsoft Research, and he's going to be talking about some of the work he's been doing over the past 2 or 3 years on opportunistic communication. For those of you who don't know Keshav, he's a pretty well-respected member in the community. He's basically played all 3 games in like researchers can play, like founded startups, work at an industrial lab, and now he's at Waterloo after being at Cornell for a while. And his name can be found on some of the seminal papers in the field as well. And this is some of the recent work. It's been generating a lot of excitement in the community that's been doing some similar stuff. And let's hear about it.
Thank you. Okay, so I was invited to give a talk at Microsoft Research in 2003 when I was just starting out on this work, and I came and gave, and I'm actually going to show you some slides I gave at the talk, and I proposed some work at the time, and then now it's about almost 4 years later, actually a little bit more than 4 years later, and I met Victor Bell at a conference some months back. He said, why don't you come and talk about what you actually did compared to what you said you would do? And I said, well, this is a good time to look back and see what happened, and that's really what I'm going to talk about over here, the case for opportunistic communication, and I'll explain what this means, and perhaps in the next hour or so, what I'll be able to do is to give you some insight into how this works. I should add that in the last few years, we published quite a few papers on this. And in any field, you go through this, what I call the first simplicity and the complexity and the second simplicity. And what I mean by that is that when you start any research problem, you look at it and you have some pretty naive, kind of dumb ideas, well, so and so should be the case. And then you start working at it, and pretty soon you realize it was pretty dumb. Things are actually much harder than you think. There's all sorts of complexity, hidden complexity, and the more you look at it, the harder it gets. And soon the system gets very, very complex, but you think that that's the best you can do. But if you work very hard at it, after a few years, at the end of it, you come to something or some insights that are really very simple. And in many cases, they actually match what you started out with. You go back to your notes, 4 years ago I said this, damn, I was right. But I didn't know I was right. I just guessed I was right. I mean, you see what I mean? And I've had this happen to me over and over again, and many research areas have gone through this first and second simplicity, as I call it. And what I'm going to present to you is the second simplicity. We worked very hard at it. And so what it really means is all the complexity is hidden away. And say, oh, that's obvious. Well, it's kind of obvious only after you do the work. So you're benefiting from a lot of work. Now, whenever I give a talk, I always start with this slide. Where the heck is Waterloo anyway? All right. I mean, actually, I didn't even know when I interviewed there. I ended up, and when I came back, I said, I got on the freeway and I got off here, but I didn't know where I was. So, well, here's a little geography lesson. You at least know where the U.S. is, and that's Seattle somewhere over here. There's a part of Canada that is south of you. So we are actually 4 degrees latitude south of Seattle. So I have to fly north to get here, which is not too surprising when you look at the map like this. If you look at this rectangle or this square and zoom in, you'll find that there is this portion of this, of this has Toronto over here and Detroit on the other end, this kind of triangle sticking into the U.S. And if you focus in over there in that triangle, then you have this square over here, and that's the town of Kitchener, and Waterloo is right over there. And perhaps the best way to understand, Waterloo is off the map. It's not really there on the map. I couldn't find a map. But so now you know where it is. And it's between 3 Great Lakes, and we're 1,000 miles from the ocean, so it's not anywhere close in the ocean. But the easiest way to explain where Waterloo is to give you a picture of what a Canadian looks like, a typical Canadian citizen of indeterminate sex for about 8 months out of the year. This is what we look like. Not too much different from a typical Seattle person, actually, come to think about it. But this is our typical Canadian citizen. And actually, it looks like this in summer. And what we're most famous for is whiskey and blackberries. Seagram whiskey was actually started in Waterloo, and blackberries made there. Interestingly enough, it's not made in China. It's actually made in Waterloo, physically, in a plant across the street from me. And so we do a lot of wireless work because of that. And MapleSoft, which is a mathematical processing language, OpenText is a decided XML actually, SGML and XML, and 2 big insurance companies. And I should probably add quite a few other companies that are now in the news. RapidMind, which does parallel computing and so on, and What4 and Whatcom are the old ones. All right, so having said all of that, so now you know a little bit about the place. What I'm going to talk about is a look back to 2002, and I see a few people here who were there in 2002. I'm going to kind of present the same slides again. No point in making new slides. And then I'll talk about a different approach to doing research, which is what applications can I build? Okay, because very often in computer networking, we're always optimizing that 5%. I got this thing, I'm going to optimize 5%. But it's always good to see, well, why are you optimizing the 5% for? What can you do with it? And that's what I'm going to talk about over here. And that will lead to a taxonomy of applications and some application requirements, an architecture that solves these requirements to some extent. And then go back and see, does this architecture meet the requirements or not? And then quite some open problems. So feel free to stop me at any time. I'd be happy to take questions. All right, so in 2002, October 2002, I was on an interview circuit. I prepared some slides. I wanted to show you these. The first one is kind of a standard slide on CMOS, and it says that if you look at the x-axis being the year and y-axis being cost of DRAM and the MIP, cost per MIP, it's going down essentially exponentially. It goes into log scale. And it was already clear back then that because CMOS does imaging and memory and RF and logic, it's clear that you will have devices which will merge computing, audio, video. So you'll have a cell phone, a flash memory, RAM, processor, video camera, and MP3 player. All of this will be the same thing. And indeed, that is the case today. This was quite blindingly obvious. And I'll go out on a limb and tell you that based on this curve, in 2018, January 2018, you will have in your pocket something that runs at 40 gigahertz and has a terabyte of storage. Okay, sounds crazy, but that's what it is. A terabyte and 40 gigahertz. So a supercomputer in your pocket. Is that a supercomputer in your pocket, or are you computing? So, okay, the second one is, this is a slide that was prepared by Craig Barrett. I stole it, but I give him credit over there. Copyright Intel. And it shows their vision of wireless inside the house, wireless in the office, and wireless everywhere. So basically, the second big picture is wireless is going to be everywhere. And this was what they were calling war chalking. I can't remember what it was anymore. But they're drawing chalk marks showing open Wi-Fi access points. They don't do that anymore. I don't know, but it's just an example of how things are doing. The third big thing was data centers aggregating resources. Now, at the time that I was proposing this, it was the academic community really wasn't engaged with data centers in any way. But now this is, a lot of people are working in this area, so I don't need to talk too much about it. These are just some pictures of data centers. And this is the punchline. Okay, there are these 3 big trends, 3 big waves that are converging. So what happens when you put them all together? And the idea is what I call tetherless computing. It's ubiquitous mobile devices. That's because the CMOS will communicate with resource-rich data centers because, well, everything is in data centers today, or wireless networks. It's pretty obvious. So the question is, are we there yet? These are slides I made in 2002, and I don't know. What do people think? Are we there yet? Do we have it? Have resource-rich data centers, wireless networks, mobile devices talking to each other? In some places. And certainly, so with smartphones, with Windows Mobile smartphones, BlackBerry, whatever, you certainly have these things. But something is missing. We have all the elements. We have all the ingredients for baking a cake. We have flour, we have sugar, we have butter, but there's no cake. So what's missing? What's missing are these applications. Okay, we don't have all the applications we have today are kind of the same old things. You have email and calendar on your mobile, and you can look up the web. If you have very good eyes and very pointy fingers, you can actually do something. But it's nothing really interesting. It's the same old, same old. So how about 3 new applications? In fact, how about 3 new classes of applications that are completely new? The first one, for all of these, I'll assume that you can do opportunistic communication. Just wave a magic wand, and any node can communicate with any other node opportunistically. So if you're in the same vicinity, you can communicate, and we'll ignore everything else. It just happens magically. So what can you do with it? Well, how about this? Wireless peer-to-peer video distribution. Okay, so what you do is you take your cell phone, you take a video of it, and you tag it. You can tag it with GPS, you can tag it with your name or whatever keywords you want, and you create a metadata list which says, this is what I have, and then you say this is what I want. Or you can do it for music. You can say, I like blues, and I have jazz, I want blues music by so and so person, and you keep it in your pocket. As I am giving this talk, my cell phone talks to your cell phone, we do this wireless peer-to-peer thing, and at the end of this talk, I have all the music I want. Goodbye to censorship and the RIAA. Okay, so this is the application which is building on opportunistic communication. There's no data center involved in this, but certainly this is feasible. Here's another kind of application. Yeah?
I was just going to say, I think Algorithmic is actually doing this right now.
Okay.
I read an article over the weekend that they've actually created their own version of MyTube.
Do they have a research lab also, or?
They're actually distributing video via their own sort of version of YouTube.
Okay.
They can actually export videos via mobile phones.
I just want to know, do they accept grant applications or not? Just kidding. But actually, this turns out to be very easy to do. And I'll come back to it. I'll tell you how easy it is. It's actually a remarkably easy thing to do. You just have to think about it the right way. The other thing is what's called drive-through internet. There are people working at it, and certainly at Microsoft, but also at Helsinki and other places, where you have used this roadside wireless access point to upload and download data. It turns out you can do quite a bit. You can upload almost 50 megabytes at 110 kilometers per hour, which in this country is 70 something miles per hour, give or take. And that's quite a lot. So if you drive past your Starbucks, you can pick up your email. Well, that's pretty neat. And you can use this to upload and download pictures and videos. And actually, that has some commercial value to it, because people who do municipal, we talk to municipalities actually, which do pictures of potholes, high-def pictures of potholes, because these need to be brought to court in case you sue the contractor saying you didn't do a good job. And similarly, construction sites, there are many other uses which I can go through. And you can download pictures. It turns out real estate agents really like this a lot, because you can download video clips of scenes of houses, and you can go and have a client to showing them places and say, oh, okay, here's something I want to show you, and it's on your cell phone, you just show it to them. Again, this is done through opportunistic download. And finally, this is a project that I've been working on at Waterloo for the last 3 or 4 years. It's called KioskNet, and the idea comes from MIT's DarkNet project from 2001, where you have a bus which has a Wi-Fi router on it and some storage, and a kiosk in a rural village somewhere. And what it has is the ability to opportunistically send messages over here. So these villages may not have any coverage whatsoever, but you can go into kiosk, enter data, and then the bus picks it up and drives it. When it goes past a gateway, an access point, goes to a proxy and into a legacy server. Now this is something that they did as sort of a demo, and they commercialized it through a company called United Villages. What we've done is to take that idea and essentially explore it to quite some depth by doing things like adding a naming and addressing architecture, so that you can send, so these guys have email addresses that you can get to, and worry about reliability, robustness, routing, etc., etc. So I'll talk a little bit more about this when we revisit it. The essential point is that this is enabled by opportunistic communication. This is an opportunistic communication app, because this path over here and this path over here are both opportunistic communication paths. So if I have the magic wand that says I have opportunistic communication, I can actually build this app as well. Again, all the bits and pieces are there to do it, but people just haven't done it. So what I'm proposing, therefore, is that the ability to do opportunistic communication allows us to do different kinds of apps, new apps. All right, so I showed you 3 apps. Is there something going on? Is there something deeper? And I believe that there is a taxonomy. So let's first look at what's common to all these apps. So one thing that's common to all of them is that they need this notion of non-intrusive opportunistic communication. And I didn't hit upon non-intrusive when we started this work. We're just focusing on opportunistic. But non-intrusive is critical. When you're driving past a Starbucks, you don't want to sit there fiddling with your cell phone saying, turn on the Wi-Fi, turn off the Wi-Fi, turn on the Bluetooth, turn off the Bluetooth. It's not going to happen. It has to be essentially semi-autonomous, and it has to be non-intrusive and opportunistic. The applications need to be disconnection tolerant, because there are going to be situations where you don't have communication. Opportunistic communication means that the opportunity ends right, by definition. And therefore, the applications need to be rewritten for this, or you can use applications, pre-existing applications that are disconnection tolerant. For example, email, or IM to some extent, or any kind of transaction-oriented application turns out to be, for the most part, disconnection tolerant. Now, the applications I'm proposing all require high bandwidth requirements. The reason is because with current GPRS or GSM coverage, you can get low bandwidth pretty much anywhere. It doesn't cost too much either. So this only makes sense for those applications that have a lot of bulk data transfer requirements. And we need applications that are tolerant to both delay and delay variance. Again, if you want like voice, streaming voice, this is not a good thing to do. So in this note, I'll mention that there's this whole branch of work called delay tolerant networking or disconnection tolerant networking, DTN, which is similar in some respects. Now, opportunistic communication is taking a slightly different view. What we're doing is taking a sort of a application-focused systems approach. DTN is looking purely at the network layer. And the differences will become obvious a little bit further when I talk about the architecture. Yeah?
So if you're assuming that you always have some sort of a low bandwidth, always on channel, and your application is delay tolerant,
yeah.
Not just trickle the data.
Because, well, one thing is if it's high bandwidth requirement, then you don't have enough bandwidth. And second thing is the low bandwidth channel is it can be expensive if you do it for a lot. So I'm thinking of SMS actually, which is what we use for a control channel. So you can do a reasonable amount of stuff. It's good as a control channel. It's not good as a data channel, other than some special data. And then finally, you have to be low cost. All these applications tend to be cost sensitive. If you were not cost sensitive, you could just use a satellite phone, or you could use whatever UMTS or HSDPA or your favorite acronym mixture. Okay. All right. So how do they differ? But they do differ from each other. And the easiest way to think about them is to think of them as one hop or one hop to ferry or multi-hop. So one hop basically means you have a node which is either connected or disconnected from the infrastructure. So the infrastructure is this big 680 million node thingy, and then you have these disconnected nodes sort of buzzing around. It's like a cake and there's flies buzzing around. Okay, that's the model of the internet for the future. Right? So these flies are either one hop away from the big cake. That's the one hop drive-through stuff. And this has been looked at, people have looked at it for a long time. Like, for example, all the TCP migrate work and ROCs and racks and even some of the overlay network from like HP Cooltalk is this kind of thing. You can you're transiently you're in front of like HP Cooltalk. You have a picture in a museum. There's an AP behind it. You stand in front of the picture and you opportunistically communicate with it. It says this picture is by Rembrandt and whatever. So that's one hop. One hop to ferry means there's a distinguished node called the ferry, which has certain geographical movement, and that's been explored by the Georgia Tech work, the Data Mule work from University of Washington, and of course our own Kiosk network. And finally, we have this notion of more than one hop. We have this crowd of people who give stuff to each other in some fashion, a mobile bit torrent, if you will, and we can use it for video distribution app, as I mentioned earlier. And most prominently, the Haggle project in Europe is looking at this as a consortium of about 10 places. The Diesel network at UMass, ZebraNet, which is Princeton, and DSRC is this IEEE standard for vehicle-to-vehicle communication. It's also looking at this. But so you can sort of have this rough taxonomy, but they all underlying the underlying communication pattern for all of them is in fact opportunistic communication. Okay. All right. So so we've seen some applications, and now I'm going to kind of change gears and go into a little bit more technical things. What are the requirements? Okay, I had this magic wand and said, all right, make it so, let there be opportunistic communication. But once you start looking into it, you find there's some pretty difficult requirements. To start with, it has to be legacy compatible. You cannot build anything and say, I'm going to change all the routers, all the switches. It's not going to happen. Okay, so we want to overlay it on top of existing TCP/IP and make minimal changes to clients and servers and no changes to intermediate routers. Okay, that's really the number one criterion for this to be successful. We want to minimize device power usage, right? For example, you can't leave the Wi-Fi on all the time. Yeah.
Something about the legacy compatibility. When you define like disconnection tolerance as like a goal, it seems like if the underlying transport protocol itself is not disconnection tolerant, like no matter what application you build on top of it, it's not going to do well.
Yes, so that, I can rephrase that by saying that if you assume that your transport connection is end-to-end and it's not disconnection tolerant, then you have trouble. But we don't do end-to-end, we do hop-by-hop transport.
Well, some thing like the wireless environment, like TCP itself, I don't know, it's in opportunistically, even
Yeah.
in one hop, it's not guaranteed to.
I didn't say you have to use TCP. You can certainly do UDP with erasure coding. Yeah. I can use UDP. No, I can use UDP, for example. I mean, yes, TCP or wireless has problems. UDP or wireless can overcome these problems. That's a whole other research area. But I'm just saying, I don't want to change anything. And yes, Jitu is exactly right. I just said, I'm not going to touch that can of worms. Let somebody else do it. It's not going to be me. We want to minimize device power usage, and that actually imposes constraints on Wi-Fi. We want to maximize use of communication opportunities. So I'm going to drive past this AP, or I'm going to be in the vicinity of somebody else for, let's say, 5 seconds, or 1 minute, or 2 minutes. Every second counts, or every millisecond counts, actually. So you can't just do the thing like, okay, I'm going to do an association request, and the wireless thing is flaky, so I'm going to drop the association, then I'm going to go to timeout. And then the timeout is hard-coded to be 5 seconds, so I do that. And then I do a DHCP timeout, and then I do a TCP timeout. You're going to waste time. So to maximize user communication opportunity requires a very detailed understanding of the RF system, environment, as well as everything above it, the MAC, IP, TCP, all the way up, DHCP for that matter. And this turns out to be quite complex, and much of our work has really gone into understanding this, and it is really quite a lot of work. Autonomous NIC management basically says it has to be non-intrusive. Okay, if it has to be non-intrusive, we have to do two things. One is you have to find the NIC that's available, but that's not that easy, right? You get a beacon packet from an AP that says, hey, I'm an AP, come and use it, but the signal strength is low. Maybe I shouldn't be using it. Maybe it's just a stray packet. We've detected stray packets from APs 1.5 kilometers away from our experimental AP. And it somehow got there. I don't know how it got there, but we found it, right? And it was not supposed to travel that far, 1.5 kilometers away and 10 buildings in between on the campus, but it got there anyway. If I say, hey, I found an AP, let me use it, I'm making a mistake. But as you can see, there's a very difficult line to walk. Now in the future is also interesting. It says, it may be a good idea for me to not use the connection right now. So let's say I have some email, and let's say the email has an attachment, it's a large attachment, and I can send it on GPRS right now, or I can send it on Wi-Fi when I go home. And maybe it's an email that's not very important. I don't really mind waiting until the evening because on GPRS it's going to cost me $10, and on Wi-Fi it's going to be free. If you think about it a little bit, what I'm really saying is this. I have a benefit in terms of utility from sending the message which does not decline with time. It's practically flat with time. All right? And I have a cost which is variable. The cost is high now and low later. So if I take the benefit minus cost, it maximizes the deferring transmission. In other words, what I really have over here under the guise of autonomous NIC management is a very hard scheduling problem. Because I'm going to schedule transmission opportunities not only now, but in the future. But then, how do I know the future? I have to think about how do I predict the future, and then I have to say, well, there is some probability that there will be a Wi-Fi availability in 2 hours from now, and then I'm going to do stochastic optimization of the schedule. And very soon you run into very hairy mathematics, which is really what we're doing right now for this. Okay? So this requirement turns out to be, again, very deep. This one is straightforward. You want single and multi-hop. Again, it's easy to express, but there are some fairly abstract problems when you get into multi-hop communication in terms of routing. Which route do you take? I mean, and the routes are all on temporal graphs. The graph structure itself is changing over time. And so what you end up having to do is some kind of limited flooding, and the control parameter is the time to live. Okay, and you have very small time to live, you'll have a small degree of spread. And if you have larger time to live, larger degree of spread, more wasted communication resources. And this actually is a pretty open problem, how to do this properly. And but you have to do it if you want to get the multiple hop thing to work. Session persistence basically is a simple concept that as you drive past several Starbucks, you want to continue to maintain progress. And this turns out to be trivial. It's no big deal. We do it for FTP downloads today. I just put it in there because you need to do this. And you have to worry about mobility and disconnection. So your IP address changes. Again, that's trivial. Use HIP or use I3 or use your favorite protocol. You can get rid of all of that. Just separate location and addressing. Very well understood problem. And over-the-air security, you have to worry about it in some fashion. And I'll explain how we do it, but there are certainly other approaches as well. If you look at it, this sort of bill of goods you find that this is at the physical level. And this is at the MAC level for the most part. This one is at the MAC, so device driver kind of level. This one is routing, network layer. Session persist is session level. I didn't talk about timeouts and retransmissions, but we need that as well, transport layer. We got every layer of the stack covered. What this really means is that what we've done is to make disconnection first class. We're saying that disconnection is really going to be an implicit or an explicit part of the system. Every node needs to be aware that it might be disconnected. And therefore, we have this routing on a temporal graph. The graph is time structured, and it affects every layer of the protocol stack. So the opportunistic communication really requires a complete rethink of everything, ranging from naming and addressing and routing and sessions and timeouts and retransmissions. Everything you've studied about, you have to rewrite the book. Okay? And that's what makes this hard. And that's what makes it a really interesting and challenging problem. Okay? So I'll stop here for any questions before I kind of move on to our approach to a solution. Yeah?
What are you thinking about, like, is it useful at all now to think about layers as the protocol stack at all?
Well, as you can see, I am showing layers over here. So I mean, there's
Things a little bit like when you divide those things into layers, it seems a little bit artificial in
Yeah.
a sense. To me, like, for instance, like minimizing power usage and autonomous link management,
yeah.
they seem pretty well tied to each other.
Yeah.
Right? Like you can't really partition those.
We've been on both sides of this by now. Okay. Haggle project, for example, is a completely non-layered architecture, and they have this notion of data manager, forwarding manager, routing manager, etc., etc. Each and the 6 managers which communicate with each other. Very complex. It becomes practically impossible to write applications based on that. So initially we started with sort of a cross-layered design, then we tried to adopt the Haggle non-layered design, and now we finally ended up with the simple layered design. But with certain understanding that some things have to cross layers, and we've been. I'll show you what it is. Yeah, sure.
I'm curious as to how you compare what you're talking about with the net news that we're doing.
Yeah, sure. Yeah. So actually, you should have asked about email, because email does the same thing too. SMTP. Both NetNews and SMTP distinguish themselves in a couple of which are different from this in a couple of ways. One is that this is very much wireless oriented, so things like minimizing power usage is not something NetNews really care about or can care about.
They care about time, because originally it was using long distance.
No, I'm aware of that, but it doesn't have to worry about device power, right? You don't have to worry about the fact that I have association requests and all this other low-level MAC stuff. The second thing is that routing in Usenet and in SMT in email is kind of hand-coded, right? With Usenet, you sort of say, well, Usenet is nothing more than a distributed pub subsystem, right? And say, okay, I sub, and does anybody have it? I can't actually direct the routing path, and as I'll show you in a little bit, you need to do that. So the addition of routing makes a huge difference, because some paths are different from other paths. With Usenet, you don't have a scheduling problem, because you only have one link, right? Here I have. What I mean by that is, when you're talking to somebody, I only have one link to get to the next node. Whereas here I can talk to you by GPRS or Wi-Fi or Bluetooth or even wired connection. So I have a choice of paths or different technologies with different cost and benefit ratios. So it's a multi-path selection problem. And in Usenet, you never had at least as I recall, you never had this notion of deferring things until later, because the costs were not time sensitive. Okay, if they were, I know that not Usenet, but there was this thing which was a different one where you would use dial-up at night to save on long distance charges. But that is a kind of a very simple day-night kind of thing, dial-up at night to save. But I think that this is reminiscent in many ways to UUCP and Usenet and SMTP. But think of this as SMTP with dynamically updating MX records, so that we can actually flip the MX records around dynamically. That's another way of thinking about it. So yes, we have actually done our homework and read through all of these old things, and there are significant differences with all those underlying things. We can't just use them. Certainly we've incorporated as many ideas as we can from the past, but there are not complete solutions that we can use. Any other questions? Okay. All right. So what is the architecture? I'm going to do the architecture in actually just two parts. The first I'll give you the big picture. So the big picture is this is what you're trying to solve over here. So we have some legacy server and we have this device, and in location 1 it has two NICs. It has a 3G and a 3G coverage, which is big, this big circle, and a Wi-Fi coverage in this green circle. In location 2 it has only 3G coverage. Location 3 it has no coverage. Location 4 it has a different AP, so it's IP address change, it's location change. And so what we want to do is to have session persistence, opportunistic communication with in the back end in this case. This is sort of your one-hop system over here. The only thing really I want to take away from this is that one is that the communication things change, and second, to do that we need to have a proxy. We need to have somebody which is hiding the back end from this, because the back end is not aware of the fact that you keep changing around, that the session is not persistent. Okay, so session persistence requires introduction of a proxy. That's basically the takeaway from this over here, and it should be pretty obvious that that's the case. Okay, so now what I'm going to do is to really show you what we do on the cell phone and on the proxy, kind of build up the stacks in parallel on both sides. So, well, that's it. So what we do is let's look at the raw devices we have. Your SMS, your GPRS, your Wi-Fi, perhaps WiMAX. The proxy is the same, except it also has a wired connection on the back end. Now you may object the proxy actually doesn't have SMS and Wi-Fi and so on. That's true. These actually are at a gateway. All right, but I'm just showing them over here because it's convenient to do that. What you can, when I say it has GPRS, what it really means is the proxy has access to some gateway or some access point which provides GPRS or Wi-Fi, whatever. And but you know, from this perspective, they're really the same thing. Now on top of this, we put something called connection objects. A CO over here is nothing more than a device driver. Okay, except it's an application level device driver, which is sitting on top of TCP/IP, and the TCP/IP connection is actually bound to a particular NIC. So I can tell the GSM CO, go send this packet, and it will actually use TCP/IP with GPRS and send it out. And similarly, I can send something over here, and it provides just a simple read-write, connect, disconnect functionality that you'd expect from a device driver. It's application level device driver. And that makes it legacy compatible, because what I'm really showing you over here is that I've created essentially a set of overlays over all the underlay communication paths. Then the other thing I need is, well, I need a TCP/IP stack on wired. That's nothing special there. And then I have to worry about the fact that data may not be sent now. It has to be sent later, because I'm going to wait for the Wi-Fi to show up. Obviously, it means I have to store the data somewhere, so I need a data store. In practice, we can use a file system, or we can use a database. We use JDBC with MicroSQL or mini SQL. I can't remember what. Now, the other thing we need to do is for each CO, we need to listen. We need to say, is it available or not? So we are sort of looking at the link and checking the link availability. And this is it has to be smart. It has to have hysteresis built in, so we don't look at stray packets. Moreover, the per CO listener actually is a little bit trickier than that, because when you get one SSID from one AP on Wi-Fi, that's just one CO. But if you have different SSID with a different AP, that actually is a different CO, because those represent different transmission opportunities with different perhaps costs and different availability and so on. So this is a little bit more sophisticated than it appears over here. But again, it's necessary. You can't not have it. Above this, we have what we call a message bus. So what I've done is I've designed this architecture essentially as a mini switch inside. Okay, so all the communication between the COs, from CO to data store and so on, it goes over a bus. It's a pub/sub software architecture. And above this, we have the really complex piece of software called the scheduler. So what the scheduler does is it gets messages from the data store saying, I have something to be sent out to some destination. It has messages coming in from here saying, I got something. And it kind of figures out when to send this message and on which NIC, and either defer it or send it later. So normally when you do scheduling on a switch, you have an output queue and you have a bunch of users, many users, right, who are contending for that single output queue. So you do whatever scheduling you want to do. Over here, we have a single user with multiple NICs, right? So it's like a multi-queue situation. Plus, we are scheduling not only for the next time instant, but for several hours in the future. Now, the problem gets even more complex, because there are actually two sources of uncertainty in the problem. Over here, the NICs are not always available. So the NIC availability is probabilistic. Moreover, we don't know about future arrivals of traffic from this side or from this side. Send and receive traffic that you're going to send. You take a picture an hour from now, well, that changes your input. So because of these two sources of uncertainty, what we really end up doing is frequent rescheduling. So we schedule all the data that we have available for now, and then if new stuff comes in, we rerun the entire scheduler. And this scheduling looks more like optimization. In fact, it's what we do is over here is linear optimization, and then we do stochastic optimization is what we're working on right now. But this looks more like optimization than your standard scheduling going on over here. And it is actually a very complex problem. Now I mentioned that you need to know about the future, so you need predictions, we need a predictor. And what the predictor is doing is things like, well, this guy was at 5 p.m. at home, which has Wi-Fi, and it's now 4:30, so in half an hour he's going to have Wi-Fi if he does the same thing that he did every day for the last year. Okay, so turns out human beings are actually quite predictable, except when they're unpredictable. Okay, what I mean is that chances are pretty good that between midnight and 5 a.m. you're at home. Okay, but when you're traveling from, let's say, 8 a.m. to 10 a.m., you're completely unpredictable because who knows where you are. And if you're not in Seattle, you've gone somewhere else, then you are in fact unpredictable. So either you're very predictable, you're totally unpredictable, and those are very nice systems and easy systems to model. And again, that's some current work we're working on mobility prediction based on these insights. And now we are kind of ready to talk about applications. So how do applications work? So Kevin Fall in his paper on DTN in 2003, SIGCOMM had this very interesting observation that application writers should not be allowed to do request response type, write programs with a request response on DTN because it doesn't work. You have to break that. So to enforce that, we use this over here, directory. So to send a message, what you do is you drop a file into a directory. It's called the upload directory. And the directory watcher grabs it and then sends it into the stack, actually puts it over here, tells the scheduler you have some more work, scheduler reruns something, allocates when it's supposed to go out on which NIC. That's what's going on. And when something arrives on the other end, then you essentially call a handler and say, go do something, you got some more extra work to do. What this means is that from the perspective of the programmer, all they're doing is writing and reading from directories. And this makes it very, very easy to write applications in this environment. So for example, I had a student who built a YouTube pub sub system. So you can say, I want all videos with so-and-so tag, and the proxy takes the tag and gets the stuff from YouTube, puts in the directory, it makes its way into the cell phone, and then it calls it over here and says, you have a new video, and then you sort of show it. Okay, and it took him about 2 hours to learn how to use the system. He built he built a working kind of a thing over here in about a couple of days, and then the rest of the time was spent in hacking into YouTube so that you can use wget to download videos because they keep changing the API. So he had to do all sorts of funny stuff to get it. But this part really worked, and we built about 15 applications using this, including things like distributed LS. You can type LS over here, and all the cell phones will respond back, with the equivalent. The handler will, list the file contents and so on. We've done database dissemination because we actually have a security architecture, which I won't have time to talk about. But we actually distribute from the proxy to all the endpoints, sort of white pages of public keys, so that people can use that. And so there are very many other things, but they all use the same paradigm. Create the object, drop it into a directory, it magically appears sometime later at the proxy, and the same thing happens over here, and then it sort of works. So one application which we use as a demo, which we showed at MobiCom 2006, was you take a cell phone and you take a photograph with your cell phone, you put it in your pocket, you walk past an access point. When you do that, it goes down to the data store, to the Wi-Fi, out to the proxy, and over here the per application directory gives it to a plugin, and the plugin goes and calls Flickr and uploads it, and the photograph you took shows up on Flickr, which is kind of cool, except you're putting all sorts of photographs of pencils and desktops and test photographs in Flickr from our project, so you can actually, we're polluting Flickr at this point. Okay, any questions about this? Because this is pretty much the guts of the system laid out for you. And it's all done in Java, and it's open source and, full of bugs. But it's, we have been using it more or less for the last couple of years now. Okay. All right, and I should actually say that this represents the third version of architecture. We did 2 other architectures which were not as clean, and now we got to this super clean state through a process of very complex intermediate states. Okay, and we need a control channel because we want to send something, you want to know it got there, so we need a sort of a private control channel. That's what the transport layer uses, for example, to do timeouts and retransmissions. Okay, so let's go back to the applications. Can I actually build these things? So the first one was this wireless P2P. So we called it MyTube, and I was teaching a course last winter at Waterloo, and I had 100 students. I broke them up into groups of 25 and said, go build this. It's a course project. And they took 10 weeks and they actually built it. Each of them was successful in building it. And they did the right, obvious things. They built a listener, they built the connection object, we gave them the message bus code, and they did all the other stuff, segmentation of videos, etc., etc. Once you know what to build, it's actually not that hard to do. Okay, the scheduling part is hard, but they didn't do any scheduling. And they assumed the Wi-Fi was always okay, so they made some simplifying assumptions, but it actually works. Okay, and it was done in 10 weeks by teams of 25 students. The drive-through internet work is something that we've been looking at quite a bit for about 3 years now. And OCMP supports it. Now these are actually sort of 2 different research projects. We need to take all the insights from this work and kind of plug it into OCMP. We haven't quite done that yet. But we've been focusing mostly on the interaction between the physical MAC and TCP layers. We had a paper in Mobius describing that. And now we're looking at a theory of optimal data rate selection. And this is joint work with Dave Hadaller and Tim Brecht, who is a colleague at Waterloo. And then this KioskNet work is the third project. And this has really been the focus of my attention, almost all my attention for the last year or so. And we've been looking at how do you get connectivity in villages at very low cost. And Tom Healy's in the audience is here. And actually, he was instrumental in getting me funding from the Microsoft Digital Inclusion Project. So thank you. And this is what we've been doing. We've been taking that opportunistic communication core, the same code that runs on smartphones actually runs on these embedded systems in villages. Okay, the same identical code. I find it's almost hilarious to think that, these guys are getting, what you would think of as cutting edge research code is running in these dusty villages. They have no idea what they're getting. And we deployed a prototype in May 2006. We released the source code. It's all open source, free, and there's no license, etc. In July, and we're doing a second release sometime this month. We're working on the last few bugs to be fixed. This one really highlights the difference between research and practice. In research, you say, well, opportunistic communication, here's a prototype. But to actually get it to work, you have to worry about things like the user shows up and says, okay, sign me up. What do you do? You can't have a grad student going there, going and modifying whatever files are supposed to modify. We had to build a GUI. The GUI has to be able to take people's names, their, whatever information about it. Then we had to create for them automatically public keys and private keys, locationing information. We had to set up a file system which is secure because the kiosk owner is probably going to snoop on it. So how do you protect that? So we use encrypted file systems to do that, so the kiosk owner cannot do that. We have to worry about, there's not enough power. So every once in a while the system goes down, so everything has to be saved in file system. And you have to worry about copies of that. It's dusty, so can't be any moving parts. We don't, for the PCs, terminals, we use recycled PCs. We don't use the hard drive. We just use only the RAM and the keyboard and the screen, and then it pixie boots off of the embedded system, which is in an enclosure with no moving. It has a disk, but it has no keyboard, no mouse, no nothing. It's a locked box with a padlock on it. Okay, this is what protects the disk. So that's our security solution, and that seems to work. And we allow connectivity on any available network. We can use buses going past, we can use GPRS, we can use dial-up, we can use VSAT, we can use long-range Wi-Fi, no matter what, because all of those are just connection objects, right? You just add in the connection object, tell the scheduler there's a CO available, go do something, and it does the right thing. So that's the power of this approach. Once you figure it out, you can actually do this pretty fast. And I already talked about security. So about 15 students have worked on it since 2005. At this moment, I have about 6 students working on it still, and it's taking quite a bit of our time. And if you just Google the word, use your favorite search engine, Microsoft Live, to search KioskNet, you will find everything about it. Okay, so have we solved everything? No. Absolutely not. Okay, there are a bunch of open problems. So, for instance, I'm going to throw out some very interesting things, some of which we're working on, some of which we're not. How do you know when to turn on your Wi-Fi? Okay, if you turn on your Wi-Fi and sniff the air, there's nothing there, you wasted it. So you kind of wasted the Wi-Fi opportunity. But if you didn't turn it on, how do you know it's there? So there's sort of a chicken and egg problem. And one approach is to use history. So well, in the past, at this time, so and so person did this, and you have to worry about how to balance history and privacy, and there's quite a few interesting issues over there. The scheduling multiple NICs problem. Now we have a solution that's optimal if we know the future perfectly. Now, not knowing the future perfectly is an unfortunate problem. So if we say, well, we have prediction about the future, then what can we do? And that turns out to be a problem in stochastic optimization. And so I talk to the people at Waterloo. We actually have a department of combinatorics and optimization. Okay, because computer science is part of the faculty of mathematics. So I'm in the math department. And I went to my colleagues and said, what do you do? And they said, oh, this is a really hard problem in optimization. So they got very excited. And I'm hoping to actually work with these guys on stochastic optimization. This cooperative scheduling idea is something we hope to work on at some point. But the insight is like this. I'm driving down the street and I see a Starbucks. So I sent an SMS to the back end saying, hey, I'm at this GPS location and I saw a Starbucks and it was open. And so the next car driving down the street, on 148th Street says, oh, that's Starbucks coming up. Turn on your Wi-Fi now because you're going to have something. Even better, I can pre-send the data to that Starbucks so when the car goes past, you can pick it up. Because you see the bottleneck is not between the car and the Starbucks. That's going at whatever, 15, 20 megabits per second. The bottleneck is the DSL line between the Starbucks and the back end. So you got to send stuff a few minutes in advance so that when it comes, it's all ready and you can zap it over. This is like spooling in the opposite direction. Okay, so it's quite funny because you always think that the bottleneck is on the wireless side. In fact, here the bottleneck is on the wired side. We have to worry about fast network detection. That is the listener part. You see a couple of stray packets. Well, is it really there or not? Credibility and routing. Well, routing is a problem. Credibility is a very interesting problem as well. Somebody says, okay, I'm sitting here and I want blues music, right? That's the example I use. So you give me something, but it's not blues music. It's some virus. How do I know that what I get is credible or not? And so what I've been doing is I have these very kind of vague ideas in what I call the calculus for credibility. And the short description of this is that you can get credible information from people you don't trust. So trust and credibility should not be confused. So what does it mean? You meet somebody on the street, you don't trust them. And that person says the sky is blue. You look up and the sky indeed is blue. So if somebody tells you something you already knew, okay, then that's credible. Its credibility can be independently verified. And that actually increases the trust of that person. If somebody gives you credible information over and over again, you start trusting them. So the weather person predicts the same thing correctly every time, well, your trust goes up. So trust and credibility are linked in that fashion. And so there are some other kind of deeper connections with information theory, which I can talk about later. But this is something that I hope to look into in the future. But at this point, everything is still pretty vague. Yeah.
Is this not like the search engine problem now? Like this variability thing?
Yeah. There are many implications to this. For example, this has been studied at Stanford. There's actually a credibility project which says, how do you know that a website is credible? If somebody says in the bank of Washington Mutual Bank, what are the elements of the bank, the website that make it credible? And but we actually our insights are based on that research, which is most of it's like HCI research, but we're using it in a systems approach. So I can talk about it offline some more, but yeah, it's quite a bit. It's a very interesting problem actually, and it completely pops out of the opportunistic communication part. All right, so. In a week from now, if I ask you what does this talk about, you won't remember anything. So I'm going to tell you what you should remember. There are only 3 things you need to remember. Okay, 3 things at all. First is opportunistic communication is not just some kind of bizarre stuff that only a few researchers work on. It actually enables quite interesting novel classes of applications, the one-hop, the multi-hop, and the fairy type applications. And one could argue that they should be present on every cell phone today, okay, because you can do some interesting stuff. The second thing is that while it's useful, it's hard. Okay, as I went through the list of requirements, it should be pretty clear that it requires a rethinking of the entire protocol stack, and it forces disconnection to be this first-class entity in networking, which networking people generally don't think about. And finally, just to toot my own horn, our work in the last few years has been taking some steps in this direction. We have built some real applications, most prominently KioskNet. But much work remains, and I certainly would be interested in having you and other people work in this area. It's kind of fun, and you get to buy these nice cell phones on your research budget. Okay. So thank you, and this is actually a picture of a kiosk just to show you what we've been doing there, and I'll take any questions at this point. Yeah. Yeah.
How are you guys approaching that problem?
Absolutely. From day one.
So, I know that you guys have deployed this in India.
Yes.
What are your future deployment plans? How are you going to scale it out?
Yeah. Okay, let me answer that in two parts. The first part is, how do we envisage the sustainability in the first place? The way we expect to do is we have sort of a three-tier architecture for how this works. So we provide the technology to what we call a franchisor, or it's an NGO, non-governmental organization, which has some technical strength. And then the kiosk owners are essentially small-scale entrepreneurs who take a bank loan to buy the equipment, and then they pay it off, and they also charge service fees. So it's they have incentive to have the system work. Okay. So if you go to their website, you actually see the cost structure, because their cost is essentially some electricity, some initial capex, and the cost of a field technician. So we have a field technician provided by the NGO, and each technician we found can service 20 kiosks. That's what they're doing today. So you have to pay them some essentially IT fee to keep things going, and then your amortization of the infrastructure. The capital every 18 months everything will die because of the heat and dust. Okay, that's just the way it is. So you put that into the cost equation. So you convert your capex into opex by doing a bank loan, and then you can do the monthly opex, and you can look at the target penetration to the market so as to do break even. So that's the sustainability model, and the full analysis is on our website. You can go take a look at it.
For each month in a period of time, the survival rate of the
Yes.
I just came from India and
Yeah.
talked to a kiosk owner,
Right.
and it took him 5 years to pay back his initial hardware.
That's right. You know why? Because the way kiosks are done today is all completely wrong. What they do is, first of all, they buy the most expensive machines they can because they want to show off. The second thing is they use dial-up lines, which are often down. Okay, and when the dial-up line is down, they can't get service. So the customer is saying, can I use it? No, it's down. And it turns off big chunks of the customer base. So, and then they put in CD-ROMs and things like that, they die right away. And finally, they are very bad about virus protection. In fact, they don't use any good virus protection. And so their systems get messed up with viruses very soon. Okay, so because of all these things, our design actually takes all of these into account. Okay, this is a tamper-proof box. Nobody can touch it, including the kiosk owner. The PCs that are recycled PCs, they are booting off of here. So there's no viruses because we control everything on this box. This one doesn't have any moving parts. It's just a keyboard and the screen and memory, right? And the connectivity is done through this card over here. We don't have anything going down, right? It's a terminal session, and the messages are stored over here, and then they go over here and they're carried through. So we actually talk to kiosk owners about why it is that they can't make money. And there are some social reasons as well, which I can go into in greater detail, but we are solving the technology part of things. And yes, if people buy expensive equipment that needs air conditioning, for example, this goes up to 50 degrees centigrade and won't die. Okay, we actually tested it in the field. The solar cells, so that it can be powered over here. This is a very low power thing. It takes between 6 and 8 watts. And we've actually measured the power consumption of every component of the system. We know exactly what wattage is taken by the Wi-Fi, by the disk, by the CPU, and so on. So we've done a pretty careful system design for this whole thing, both on the economic side as well as on the power budget. Now, this is not what most kiosk deployments do. They don't have the intelligence or the experience to build a system this way. They go to the equivalent of Best Buy, buy a PC, go to the phone company, get a dial-up and say, I am a kiosk. Sorry, that doesn't work. It's like saying, I bought a Boeing 747 and I brought it to my village and it doesn't fly. Well, guess what? It won't. There's no runway. There's no maintenance. There's no nothing.
I agree with you. Technology is part of it.
Yeah.
You pointed out there's also
There are many other factors. Absolutely.
creating relevant services that people really
Yeah.
want to use.
That's,
Or
yeah. You're right. Yeah.
there's a multifaceted challenge.
I fully buy into it, okay? All I'm saying is that if you don't have the technology, you're trying to run you know, you can't run. You don't have the necessary background. Once you have the technology, you're not done though.
Have you explored, instead of using desktop PCs, actually using laptop technology?
We don't really care actually over here. We just need something that will boot off of here. We use desktop PCs because it's cheap. You can buy them at junkyards, which is we bought them. This one is bought at a junkyard. Okay. Every year we discard millions and millions of pieces and put them in landfills. Why should we do that? We can just use it over here. Laptops are not in landfills yet. When they are, I'll get them from the landfill. So we use recycled PCs, we use recycled cell phones, we recycle everything. Even the slides are recycled actually.
Now, the cost of SMS,
Yeah.
and you said that you guys use SMS as your background communication.
Yeah.
Clearly there's a cost associated with
Yes.
that.
In North America, SMS is priced extortionately. In India, it's not.
It's not 1 cent.
You can get unlimited SMS plans, which are pretty reasonable. And we expect that with the MMS coming in, SMS will go to all-you-can-eat SMS for a very low price. That's sort of on the cards very soon. So we're basically targeting that. It doesn't mean that we have to have SMS. We can certainly do without it. It's just a nice thing to have, but it doesn't depend on having it. So.
And have you guys done any testing with like point-to-point over long range?
No, we haven't. There should be no reason why we can't use it because the API presented by long-range Wi-Fi is just TCP/IP. If you go back to my architecture, we designed it very carefully to make sure that it's what we call, what you can think of as being future-proof. I can slot in new COs. I just need to write a new listener for it, and I need to describe to the scheduler what is the cost and benefit. It is dollar cost and the energy cost and the benefit which actually is told by the user. Okay, once I do that, then it just starts working right away. So this is completely extensible architecture. And so we can slot it. We don't have WiMAX today. We could put it in. And so WiMAX is no different from long-range Wi-Fi. You can actually put in dial-up over here as well, or VSAT or whatever you want. So, yeah, that's part of the design to make it extensible. Yes.
Thank you. A comment and a question. First, a comment. I think many people in the room know Kentaro Tomoya and the ICTD conference, which was held in Bangalore in December. And this project has a paper accepted at ICTD conference, and I think it amplifies a lot of what you're talking
Yes.
about.
Yeah.
That might be a good paper for folks to reference.
Right. Yeah.
The question is, I didn't hear you talk too much about power.
Mm-hmm.
And I think one of the very interesting things about your project is that you're working in an environment where power is as intermittent, perhaps more intermittent than some of the networking aspects.
Yeah.
And you've taken some creative solutions
Mm-hmm.
towards power, solar panels, car batteries,
Right.
etc.
Yeah.
Can you talk a little bit about the complexity of power
Mm-hmm.
in your architecture?
Okay, so I mean, at some sense, there are two different instantiations of the architecture, if you will, right? One is on cell phones. This stack runs on cell phones, and the same stack that runs on a cell phone actually runs on the kiosk as well. Okay, so when we talk about power, we're talking about two different things. Now, let me focus on the kiosk side because I know that's where your main interest is. The way we see it is that the kiosk controller, which is this embedded device running the stack over here, is the one that should be kept on all the time because the buses could keep going past at any time. So what we've done is we measured the cost of doing this. As I said, it's about 6 to 8 watts. And there's a paper on our website, you can look it up, which has a detailed breakdown of every component, what is done. So we want to keep it going, and the way we do that is by using a car battery. And oops, that was not a good idea. Okay, I can't remember how to do this any better than this. Okay, we're almost there. But what we do is we use the solar cell to. Okay, so we use the solar cell over here to charge the car battery, and we use the inverter to power the kiosk controller. That's basically what's going on over here. Now, kiosk owners understand car batteries really well. Okay, they use this all the time. So we had no trouble getting car batteries, and we had no trouble getting them to how to do it. And since it only takes about 5 hours of sunlight is enough to keep this going for a couple of days. Basically, that's what the math is for this particular solar panel that we used. And now for these guys, the terminals use 75 to 80 watts of power right now. So they essentially work only when there is electrical power, or if they have a stack of batteries, which they actually often do. Using laptops will make it much better. But recycled laptops aren't yet coming onto the scene. But when they do, we have no problem using laptops. They would similarly boot from the kiosk controller as you normally would. Now on the cell phone, power management turns out to be far more complicated because you have less available power. But I won't go into that here. Yeah.
Mike Bass was here a couple months ago.
Okay.
We were asking him about solar power, and he was having challenges in projects that he had in Liberia where the solar panel and solar power sources are not as well understood
Yeah.
as gas power generators,
Mm-hmm.
and they're also more susceptible to theft.
Mm-hmm.
Have you run up against any of those challenges? Or just your point of view on that? Because you have a very innovative power system.
Yeah. Well, I mean, diesel power is certainly people use that. Some places people actually get car batteries on motorcycles or bullock carts even and charge them in a town and bring it back to the village because they use it for TV sets. They power TV sets this way. And for them, TV is more important than email. Okay. So there are many solutions. If you standardize on car battery, which is what we've done, then how that car battery gets charged is a local problem. And now, in terms of solar cells, this is just a suggestion. We're not saying you have to. We looked into solar cells. These tend to be fairly expensive, and you say they do get stolen. At least in India, there's a tremendous push towards wind and solar, and perhaps we can use that. What I think, what we'd like to do is to say, look, we'll support car batteries. You figure out how to charge it, and the kiosk owner can figure it out. It's something that they know how to do, and it's very, very location specific. So we don't want to get into that part over here.
You haven't had any challenges or people that are not solar panels or people?
Well, the entrepreneur has an incentive to keep things going, right? Because he's making money on it. It's not. I mean, so they protect it.
The utility electricity is not on for enough hours to charge the battery?
Yeah, that's one other thing that they do. It's usually on for at least 5 hours a day, and that gives you enough time to charge the car battery. So that's something that people do as well. It really depends on the situation at hand. So actually, you asked about scalability. Let me come back to that. The problem here is that we're trying to build a system that's usable in areas where there's no technical expertise. So everything has to be as robust as possible. At the same time, getting systems to be robust is something you can't publish papers on. It's not valued by the academic establishment in any way. So what I've been doing is I'm forcing my students to write essentially production level code, robustness testing, QA, unit tests, function tests, all that stuff that I learned when I did a startup in my lab. They don't like it because they can't publish anything on it, but they believe in the project, so they're working overtime on it and doing extra research as well, okay? But we can't sustain it. So what we're trying to do is to try and spin it out to somebody, okay? What we'd like to do is somebody to steal the idea and make a buck on it, okay? So every talk I give, I say, please take the ideas. Please, all the code is open source, all the ideas are free, everything is open. Make $1 million, keep it. I don't want a cent. Just do it. Okay, nobody is willing to do it yet, so maybe you will do it. Okay, but that's the problem. So what we're trying to do is to provide a turnkey solution, and so the second release, which we're doing in January, is going to be sufficiently packaged and tested and robust and has all this stuff. So we think hopefully somebody will take it. So we're talking to anybody who listen, and that's the big problem. There's a lot of people who express interest, but very few people who take the steps to actually deploy a solution that's a research solution.
How many kiosk operators do you have?
Right now, zero. I have a lot of people expressing interest. Oh, we'd like to try it. We've set up this quick start program. They can get a kit from us. They can deploy it. We were supposed to have deployment in Orissa in December, and there was a landslide and the roads got cut off. So we couldn't reach the village. So what do you do? So until the road gets rebuilt, we can't do it. There's another deployment we're trying to do in Madhya Pradesh, and there's some political infighting in the NGOs, so it's not happening. There's a deployment supposed to do in the Cook Islands in the South Pacific, and this guy contacted me and said, you're going to do it, and the Prime Minister approved it. They only have 2,500 people, so the Prime Minister is actually also a local janitor or something like that. It's a very small place. And the Prime Minister says, okay, but they're trying to raise money, because they have these daily flights from the central to the outlying islands. They're trying to raise the money to do this, and they have to go to a donor, which is New Zealand, and get the money. And so every situation has its own problems, and so we are trying our best. But at some point, this is not an academic problem, it's not a research problem, and we will have to throw in the towel perhaps another year from now. We've been doing this for almost 4 years now with no payoff, and can't publish, but I have 10 years, so it's okay. Anyway. Thank you.